Okay, welding efficiencies. We said last class that there are many efficiencies. There are efficiencies associated with mass, efficiencies associated with the energy, and efficiencies associated with time, and efficiencies associated with strength of the joint. And we got to talk about the mass efficiencies that related to what is lost in spatter and what is lost in slag that was never meant to be into the weld, but typically you buy the electrodes by the pound and they come with an amount of fluxes that you know you'll lose. And we went into quite a bit of detail into how this mass efficiency related to the metal transfer mode, how the mass efficiency related to the type of consumable we had, whether it was flux core or metal core or solid. We saw how this mass efficiency related also to the shielding gases, how, for example, if we have CO2, we have a globular transfer, therefore more spatter, therefore lower mass efficiency, or how in the case of flux core, we saw that if we have a self-shielded flux core, the mass efficiency is lower than if we have a gas-shielded flux core because we have more spatter in self-shielded. We saw that. Then we started to talk about energy. All this was about mass. And we talked about the thermal energy. And here I have something that in the following slides is fine, but is the thermal efficiency is how much went into the workpiece divided how much came out of the machine. Some of it doesn't get in because, for example, in the case of lasers, gets reflected. In the case of the arc, if you see the light of the arc, whatever light you see is light that is not going into heating up the weld. So there is an efficiency associated with that. And we saw that there are tabulated values that are more or less like these ones we have here in this book. And also, I suggested based on the energy rates we have discussed already when we talked about the voltage and power in arc welding and the deposition in arc welding, we saw that we can ballpark an efficiency in a way that we can account for things like, hey, what's the role of electrode extension, right? Things like those. Why does MIG have a higher efficiency than TIG? And here we did some calculations, right, in which we estimated an efficiency and was quite reasonable. We did it for MIG, we did it for TIG. And this is the last slide that we discussed last class. We talked about how we have something called weld plug efficiency. And weld plug efficiency is how much heat gets out of my welding machine compared with how much heat I took from the electrical grid. So for example, in the case of a inverter type of arc welding machines, essentially is a modern welding machine. Arc welding machine is more or less 85%. That means the machine, most of 85% of the power that I take from the electrical grid goes out of my machine. Now, not all the energy that goes out of my welding machine gets into the plate, because some of it, in the case of arc welding, is lost in the form of energy losses at the arc, right? What we lose is more or less, very approximately, like more or less 2/3 of the power in the arc column. All right, in the case of lasers, the efficiency is lower. Lasers are notoriously inefficient. In the case of diode lasers, it's about 50% efficiency, and these are very efficient. Fiber disc lasers and these lasers that are also solid state lasers, 30%. CO2 lasers, 10%. To give you an idea, in our lab, right now we have a diode laser, right? That is 9 kilowatts. That means when I'm running that laser at full power, I'm using 18 kilowatts, right? Because 50% efficiency, 9 come out, 9 get lost. But if I wanted 9 kilowatts on a CO2 laser, I would have needed 90 kilowatts. Now, 90 kilowatts, let me tell you, that's about what a small town burns, right? And if I had an ND-YAG laser, 3%. But in these lasers, the ND-YAG is such low efficiency, but also they tend to have low power. So that doesn't mean that I'll be burning the energy of 3 little towns. So I uploaded, together with this class, a very interesting paper from my friends in Germany who are studying weld plug efficiency. Isn't that amazing, right? Like you take a welding class and you expect to learn about electrodes and strength and cracking, whatnot. But some people do a living of researching welding, and they are thinking so many steps ahead. They're thinking, oh, fine about the cracking and the the heat affected zone. How about our weld plug efficiency, and what is the environmental consequence of our choices in processes and within a procedure and procedure for welding procedures? There is another efficiency that is very, very interesting, that is called melting efficiency. I mentioned this to you in passing, but here we have a formula. And melting efficiency is, if I have a cross-sectional, in a weld, I measure my cross-section that was molten, right? I wanted to melt some amount, right? And we know that in welding, the rapprochement of atoms, the joining, happens because of fusion, right? So fusion cannot be zero, can be small, can be larger, whatever it is. But this area that I fused, I need so much energy to melt that area. What is the minimum amount of energy I need? Well, is to reach to the enthalpy of liquidus, right? The enthalpy at which all the metal is molten, but not 1 degree of superheat, just that. And the rest of the metal, oh no, the rest of the metal stays at room temperature, right? That's ideal. That would be 100% efficiency. I melted what I needed to melt, and I did not heat up any of the plate, and I did not heat up, I didn't superheat any of the weld. Of course, it's not like that in reality. So we do superheat the liquid, and we also have heat spilling into the plate. That is captured in melting efficiency, and has this formula that comes from this very, very simple energy balance. But which I suggest you check. I'm not going to ask you to derive this formula, but I think you'll benefit from being able to see how it comes here. But what this formula says is that for a given cross-sectional area we are melting, the efficiency is lower when we have bigger heat input. Of course, I mean, if I have a weld, I have 2 welds, and both welds have the same cross-section, they look the same. But if one weld had a lot more heat input, the weld with higher heat input is less efficient because it took much more energy to melt the same amount, right? So I want to ask a question that I would like to hear your thoughts in the chat. And the question is, if the 2 welds have the same cross-section, but different melting efficiency, let's start with this. Which one do you think would give us bigger distortions? We have not discussed distortions in detail so far, so I'm asking only for your intuitive feel of what do you think is going to happen. We'll see the proper formulas later on in this class. But what do you think? Who has higher distortions? Higher distortions are with higher heat input, with a high melting efficiency, or low melting efficiency? What is desirable for low distortions? Well, if we have high heat input, okay. So I have thank you for pitching in. So if I have high heat input, but I melted little, that means I'm going to address the first question. Yes, high melting efficiency and low nominal heat input is what we want, because the high heat input, whatever I didn't melt, it goes so out in the form of thermal expansion that will create more distortion. So high, for a given weld, I want to use as little heat input as I can. So high heat input is typically not our friend. That said, if the heat input is too small, then we save the problem of distortions, but we can have a problem of too fast cooling. And that can result in a weld that is too fast, that can have cracking. Another comment is multi-pass bead has more distortion. I don't want to address that right now because it's unrelated to melting efficiency, but of course that's true, and we're gonna see that later. Each time I put a welding bead, there is something called the tendon force, because it acts as a tendon that is pulling the plate. And if I put more and more and more beads, I'm putting more and more and more of these tendon forces that will cause more distortion. We'll discuss that in a specific module in this class. So, which has higher, a bigger heat affected zone? High melting efficiency or low melting efficiency? I'm asking, which gives us bigger heat affected zone? High melting efficiency or low melting efficiency? Again, yes, low melting efficiency will give us a big heat affected zone, right? And that's the reason why if we do oxyacetylene welding, we end up with like horribly distorted parts that with enormous heat affected zones. And if you do laser welding, the heat affected zone is so small that you need a microscope, right? Of course, there's slightly different prices in the two processes. This is the gist, right? And also, this is very associated with velocity. And I'm going to show you later a formula for autogenous welding with which we can calculate the melting efficiency. So if you have the same heat input, you're gonna see that if you move too slow, you might end up not melting anything. Okay, there's another concept that is a concept of dilution. And dilution is how much, if you have all these welded metal, right, that is area of the base metal plus the area of the deposit, is how much of the total cross-section of the weld came from the substrate. So 0% dilution means we didn't melt anything. So probably we can have problems of lack of penetration then. But if I have a high dilution, we're not necessarily good. For example, in the case of overlays, I would be bringing in all this cheap carbon steel when I was paying for this very expensive overlay material. Not a good deal. You don't want to have high dilution. In the case of stainless, things are a lot more difficult, because if I dilute the base material, if I'm doing dissimilar metal welding and I put stainless on top of carbon steel, I dilute my carbon steel and the carbon comes into the stainless. And if you remember, carbon is not the friend of stainless because the carbon reacts with the chromium and can sensitize the weld. In addition, if I dilute the nickel in my stainless steel, I might end up having a weld that instead of finish, end up being austenitic, might end up being martensitic. Big difference, because austenitic is ductile and soft and the martensitic is hard and brittle. So dilution is extremely important for overlays, stainless steels and other types of dissimilar metal joining, in which you want to know what your mixture is going to be. And these formulas that we have here are accounting for how much we dissolve of the base plate. I want to discuss time efficiency. So we already discussed this briefly, the operating factor, and here are some ballpark values. But let me tell you, these numbers that I have here, that I got by reading and talking to people, they have such a wide range of variation. Some shops are very well organized, some shops are not. Maybe the shop is very flexible, but the price of flexibility is that things are not so handy when you're looking for them. Here we have operating factors, and I uploaded the paper written by our colleague MatE, who did this study for the province, in which he estimated operating factors for welding of pipe in this province. So here are the values that come from that paper, and we already discussed how they wrote for the case of root pass with 6010, how he wrote 0, because in reality he measured negative, and it's quite interesting result. Here's one last type of efficiency, which you seldom find in the welding books, but people use in the field. That is called the strength efficiency, the joint efficiency. And is, if you were to make a weld and then you break it, right? The strength of that joint is bigger or lower than the strength of the base material. We, right, in this province in which we use lots of things according to ASME, for us, very seldom you break at the weld metal or at the heat affected zone. Typically our welds are stronger than the base metal, typically for us. But in places like the automotive industry, right, and some other industries, they use this concept of joint efficiency. And the reason I want to bring it to you is because I was once talking with a colleague, and he asked me, okay, how would you estimate the joint efficiency in a butt joint? And I said, the joint efficiency is always 100%, right? Because if you don't break, if you break at the weld, it's a rejection. Only later on I realized, yeah, that's true for us in Alberta. But in the world, there are many other types of welding, including automotive welding, in which very often the joint has less strength than the base metal. And they can live with that, right? But they want to understand it. Funny enough, right now, we're about to have a project calculating improving joint efficiency. But an interesting thing about the joint efficiency is that this exact same joint might have different efficiencies associated with them, right? This is one plate, this is another welded. And if I ask you the joint efficiency, of course, you can test it and you have a number. But the idea is to estimate an efficiency from a design point of view, so you don't need to break things all the time. And these estimations are based on inspection. So if you inspected something and that something has no flaws, you typically assign a high joint efficiency. If that same weld that had no flaws, you don't inspect, then you're not sure it didn't have flaws. So you will assign a lower joint efficiency as an estimation, right? Even if in the end, when you test it, it would give you the same number. As you assign an efficiency from during the design process, the less inspection is the less, the lower efficiency. So here we have some kind of values. Look at this. If you're doing this butt joint in a pressure vessel and you have full inspection, like nuclear, 1, fine. You cannot have higher than 1, right? If you don't inspect it at all, 70%. Now, joints of different types, for example, these other joints here that have a backing strip, or we have a double fitted lap, right? Sometimes are never inspected, right? In the automotive industry, you barely even look at the weld. You're not going to be doing X-rays or anything. And look at the very low values that are assigned to the joint efficiency. So the bottom line is that joint efficiency for one joint is the breaking strength, right? The joint strength divided the base metal strength. From the design point of view, is what you can guarantee that joint is going to be. And the more you inspect, the more you can guarantee. The less you inspect, the less you can guarantee. And also the type of joint, the joint geometry plays a role. Here I have from ASME, right? We have been typically in welding, we live in ASME 9, but that's not the only part of the ASME boiler and pressure vessel code that deals with welding. We have section 8.2. And here they say what the joint efficiency would be for different types of joints and the different types of inspection, right? This is the same as we had before. Before it said only spot, here's spot X-ray, right? And we get to see what strength we can assign during the design of a pressure vessel. Very interesting. I wanted to share this with you. Okay.